There is something called cumulative ordering, and it means that a certain memory barrier instruction executed by a certain CPU also takes the A and B sets of other instructions into account. So the A set, I mean the set of instructions that are before or should be before the memory barrier, the A set also includes the applicable memory access instructions for made by other CPUs before the barrier is started, and applicable that is different between different memory barrier instructions. I mean, it's the ones which are ordered by that memory barrier instruction. Okay, and the B set, those which should be after the barrier, are the future instructions. And we will see that the effect of cumulative memory barriers, the lightweight and also the heavyweight sync are cumulative, but the isync is not. So if we have this program, and it really shouldn't work with the branch conditional and isync, since we need, I mean, it's not properly ordered according to the C standard, but this example illustrates how a cumulative memory barrier instruction can just happens to make this work anyway. Okay, this is not the most important part of the course, I should say. It's an illustration of very specialized detail about the power architecture. Okay, so if we have A and B as 0 from the beginning, and then this thread sets A to 1 and does a lightweight sync. Okay, and now we assume that this reads the 1 from there, and it sets Y to 0, since B is still 0, and does this lightweight sync, and then sets B to 2. And now we assume that thread 3 reads this B, meaning 2. And it does a lightweight sync, and then it reads A. And as it happens, the lightweight sync will make A be certain to be 1. But if we instead would have used the branch conditional and isync, it could happen that thread 3 instead would read the old value of A, meaning 0. Okay, and the reason for that is that branch conditional and isync is not taking, I mean, it's not cumulative. So we will now look at implementation examples for power on various C and C++ primitives, and these are from the official documents of the ISO C and C++ committees, and were created by these two researchers at IBM. But there are other implementations possible as well. So, I mean, now we come to the interesting part that we should think about when we do the different operations on atomic variables. Okay, so if we use non-atomic variables, it's always like load relaxed, meaning only a load. So then we don't have to worry about costly instructions. But load relaxed, that's just a load. load consume, it's on power also just a load. But the compiler has to figure out what it may and what it may not move to before this load. Load require, it is what we just saw. And load for sequential consistency, this is time consuming operations. So that makes us not want to use sequential consistency. And then we can think of, suppose that our code is safety critical. Safety critical code is used, for instance, in nuclear reactors or brakes in automobiles or in airplanes or trains and many other things. And it means that people can get severely hurt if there is an accident and even die, of course. So maybe it is a good idea to use sequential consistency in such situations. That may be an argument for that, but I would say it's better to use a single-threaded C program in case we have a safety critical program, if possible, of course, because it may be too costly to use sequential consistency. Okay, you may wonder why you see in the first place in safety critical systems. Actually, it's used to a very large extent. And the reason is that it is closest to machine, and the C compilers are extremely mature, and it's easier to assure that a C environment is sufficiently bug-free as compared to other more complex languages. Okay, so store relaxed, not much, and store release, that's lightweight sync followed by the store, and store sequential consistency, heavyweight sync followed by the store. Okay, and this is just a repetition of the arguments for not using sequential consistency, which I, as one can imagine now, is not very fond of. Okay, the memory fences, it's the lightweight sync except for sequential consistency where it's the heavyweight sync.